Okay, in this lesson, we're going to look at the integral of 1 over x squared plus 10x plus 29. When you see a denominator like that, the first thing you try to do is factor it to see if you can use partial fraction expansion. But you try a couple times, and you'll realize there's no way that can factor. If I have x squared here and I have 29 here, any way to get plus 10x out of those middle terms. X times x, the only way to build 29 is 29 times 1 or negative 1 times negative 29. And you see either way, there's no way we're going to get 10x out of that. If it were 30x, maybe, but not 10x. That can't be factored. So if that's the case, partial fraction expansion is not going to work. So we need to do something else. And what I'm going to do is I'm going to appeal to trigonometric substitution. And to do that, I need to complete the square. What do I mean by that? So I have dx over x squared plus 10x. What do I need to do to complete the square with x squared plus 10x? So we will do another square to complete. To remind you of this process from algebra, we have x squared here. 10x is plus 5x and plus 5x. So you split the 10 in half. So this piece, x times x, gives me x squared, length times width is area, plus 5. 5 times x is 5x, plus 5 times x is 5x. So what completes the square? 5 times 5 completes the square. So when I do that, what am I going to be left with? 5 times 5, of course, is 25. 5 times 5, of course, is 25. So we're going to add 25 here to complete the square. But I needed 29, so I'm a little bit short. How much more do I need? I need 4 more. Now, what do I have here? The thing on the inside, x squared plus 10x plus 25, is the same as what? Is the same as x plus 5 times x plus 5. Is the same as x plus 5 squared. So this piece is x plus 5 squared. So I have integral of dx over x plus 5 squared plus 4. And this is what I'm going to use with trigonometric substitution. So let's draw our triangles and do our analysis. Integral dx over x plus 5 squared plus 4. Drawing our triangle. I hope it's obvious that these two sides are legs. Remember, we're using a squared plus b squared equals c squared. We see a plus here, so one of them is a, one of them is b. Remember, a and b can be switched between the horizontal component and the vertical component. So let's say what? Let's say x plus 5 squared plus 2 squared will equal c squared. So that tells me that a is x plus 5, b is 2, and we see that c squared equals that stuff. C squared is x plus 5 squared plus 4. So c would be the square root of x plus 5 squared plus 4. So let's label accordingly. I need an x plus 5 and I need a 2. I'm thinking tangent here, if you recognize the form. Tangent is opposite over adjacent. So I want the x plus 5 on the vertical piece. So the x plus 5 is going to go here, theta here, of course. And then b is 2. 2 is going to go here. And then my third side, c, is going to be the square root of x plus 5 squared plus 4. So we've done the hard part. We've constructed the triangle. We want to do some analysis on that triangle. We will start with the simplest ratio, which is opposite over adjacent. Tangent of theta is x plus 5 over 2. If you like 2 tangent theta is x plus 5. Let's take the derivative with respect to x of both sides. The derivative with respect to x of 2 tangent theta is the derivative with respect to x of x plus 5. The derivative of tangent theta is secant squared theta. So with respect to x, that will be 2 secant squared theta times the derivative of theta, which should be d theta dx, equals the derivative with respect to x of x plus 5, which is just 1. And you'll notice I need to solve for dx, so I get that sort of automatically here. 2 secant squared theta d theta equals dx. So this is dx and will get substituted here when the time comes. Now, I also need to figure out what's happening with this thing, with x plus 5 squared over 4. So I look at my triangle and I ask myself, what is the simplest ratio with x plus 5 squared over 4? Not these two, because there's x's in both pieces. These two would be the simpler ratio. So if that's the case, what am I going to say? Well, I have this side adjacent, that side is hypotenuse, that's cosine. So we'll say cosine theta is the adjacent 2 over the square root of x plus 5 squared plus 4. And remember what we need to change out the x plus 5 squared over 4, so I need this on top. Take the reciprocal of both sides. Reciprocal of cosine theta is secant theta, is what is now square root of x plus 5 squared plus 4 all over 2. Multiply both sides by 2, 2 secant theta equals root x plus 5 squared plus 4. And then we'll finish this by squaring both sides. So square this side and square that side. If I square 2 secant theta, that gives me 4 secant squared theta equals what? When I square the square root, I just get x plus 5 squared plus 4. So this time you will notice x plus 5 squared plus 4 here is going to equal 4 secant squared theta. So we're going to make that substitution up here. This is going to become 4 secant squared theta. So we need those two facts to go ahead and finish our problem. So focus on this. Focus on the integral of dx over x plus 5 squared plus 4. Integral of dx over x plus 5 squared plus 4. What's the relevant information I needed from the previous page? We had dx was equal to 2 sec squared theta d theta. We had x plus 5 squared plus 4 was 4 secant squared theta. And we had a triangle. Let's go ahead and rebuild our triangle from the previous page. Our triangle with theta, we had x plus 5 here. We had 2 here, and we had the square root of x plus 5 squared plus 4 there. So that's the relevant information we need. Now let's go ahead and make our substitution. dx on top, 2 secant squared theta d theta. On the bottom, what do we have? X plus 5 squared plus 4 is 4 secant squared theta. And you will notice the secant squareds divide out. 2 over 4 is 1/2. So we get 1/2 integral of d theta, which would give us tell me something whose derivative is 1. The answer is just theta. So this is 1/2 of theta plus c. But what is theta? Well, if we go back to that first page, what did I say? I said tangent of theta was x plus 5 over 2. And we certainly can see that on our triangle here. If I'm looking at theta, the simplest ratio with theta is opposite over adjacent. Now, there's other ways that you could define theta. You could say arc cos, arc sec, arc sine of x plus 5 over root x plus 5 squared plus 4. But the simplest ratio is opposite over adjacent. So we'll note tangent of theta, again, is x plus 5 over 2. which means what is theta? Theta then is the inverse tangent of x plus 5 over 2. So that takes me to my last step. So we get 1/2 of theta, 1/2 inverse tangent x plus 5 over 2 plus c. So we believe that is our integral of that function. So let's look at our question and our answer just one more time. We think the integral of dx over x plus 5 squared plus 4 is 1/2 inverse tangent x plus 5 over 2 plus c. And I just want to talk about how we can check that. Check it on a graphing calculator, check it on Desmos. The way that we check it, we see is the derivative of the answer, the question. So how to check? We're going to look to see if the derivative of the answer, the derivative of 1/2 inverse tangent of x plus 5 over 2 plus some constant, I don't care what that is, does that equal 1 over x plus 5 squared plus 4? And we'll go ahead and we'll do that on Desmos. So let's pull that up. So let's look at Desmos. So here's my graph of 1/2 inverse tangent x plus 5 over 2. I added plus c. I just added plus 2 so we could see it in the window. So that is my function of interest. I brute forced the derivative by using an h of 0.001, f of x plus h minus f of x over h. And I get this, which we can't see very much. So let's adjust our window. Instead of going negative 7.19 to 7.19, let's go negative 0.2 to 1 maybe. You can see a little bit more play in the graph. So we believe that this is the derivative of my original function 1/2 inverse tangent of x plus 5 over 2 plus 2. And I hope that the derivative of my answer, this was my answer, was the question. If the derivative of the answer is the question, I've done the integral properly. So if I turn on this, do the functions match? Sure, looks like they do. So here is what I received by doing the trig substitution procedure. And here is what I have by using brute force. And that looks good.